All right, folks, let's go over some questions. So here is the first question for you. It says, if both the plate area and the plate separation of a parallel plate capacitor is doubled, what happens to the capacitance? It doubles, it's halved, it's unchanged, it's tripled, and it's quadrupled. You have 1 minute. Please talk to a person next to you and start answering. Alright, the correct answer here is unchanged. So the capacitance should stay unchanged if both the plate area and plate separation is doubled. And it looks like most of you got it right. That's very good. And that is because, if you remember, the capacitance of a parallel plate capacitor is epsilon 0, the area of each plate, divided by the separation between the plates. So if these are your plates here, these are the two plates, and the surface area of this plate is A, and the distance between these two plates is D, then if suppose A goes to 2 times A and D goes to 2 times D, do you see that C nu will be epsilon 0 times 2A divided by 2D, which really stays the same. You can see, if suppose I had told you that this plate, let's say I had told you that this is a square plate and you are not changing both dimensions, but you're changing only one. Or let's, easier still, suppose in the exam you were asked a question where you were given, say, circular plates, 2 circular plates, both with radius r, distance between the 2 plates is d. Suppose you were told r goes to 2r, d goes to 2d, what happens to new capacitance? C nu is equal to what times C old? What would be the answer here? Any thoughts on this? Everybody should be talking to a person next to them, talk about it for half a minute. So if suppose the question was the radius is doubled and the distance between the plates is doubled. Not the area. This time it's not saying the area is doubled, it's saying the radius is doubled. Alright, how many people think it should be unchanged here? How many think it should increase? C nu should be more than C old. How many think C nu should be less? Okay, in this case, let's think about it. C nu will be, first of all, what is C old? C old should be equal to, we already said epsilon 0, and area will be pi times r square. Remember, area goes as radius square, right? This is always true. Area will always go as the dimension square. Volume will always go as the dimension cubed. Volume is the amount of space inside. Area is the surface area. So area always goes as the dimension square. And in this case, for circular cross section, it's pi r square. And divided by d, this is the initial thing. C nu will be epsilon 0 pi times 2r square divided by 2d, and you can see that this thing will be epsilon 0 pi 4r square divided by 2d, 2 and this cancels out. So what you're left with is epsilon 0 pi r square over d times 2. There is a factor of 2 that is left over. So C nu is 2 times C old. Is everybody seeing? So you have to read the question before you can actually interpret what you have to do. So in one case you are being told the area is being doubled. In this case the area is actually quadrupling. Is everybody seeing that doubling the radius makes the area 4 times more, because it goes as 2r square. 2r square is 4 times r square. So the area is becoming 4 times pi r square compared to the old area which was pi r square. So this time the area is not doubling but quadrupling, whereas the distance between the plates is still d going to 2d. So in this case C nu will be 2 times C old, right? Is everybody understanding the difference between the two cases? Okay. Let's look at the next question here. Okay, it says a solid spherical conductor is given a net non-zero charge. The electrostatic potential of the conductor is largest at the center, largest on the surface, largest somewhere between the center and the surface, constant throughout the volume. Please talk to a person next to you. You have 1 minute to answer this question. Okay, you have to give your name at the end and write down your answers on paper. Oops. Okay, 6 seconds, folks. 3 seconds. All right, the correct answer here will be what? Yeah, constant throughout the volume, because this is going to be an equipotential surface. Remember, the conductor is going to be an equipotential surface, and so the potential everywhere inside should be the same. So if you put some charge here on the surface, and even if it was not spherical, in the case of spherical conductor, the charges will uniform distribute themselves so that the electric field is 0 everywhere, right? If the electric field is 0 everywhere, what we said, if you remember, the change in potential was negative of integral E dot dl from the initial to the final point. So if the electric field is 0 everywhere, so suppose you are going from here to here, suppose this is your initial point and this is your final point. If you go from here to here, if the electric field is 0 here, 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 everywhere, don't you think this integral, this line integral, which is basically adding up E dot dl here, 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 will add up to 0 if E is 0 everywhere anyway? That would mean that V final minus V initial is 0. That means V final must be equal to V initial. That means the potential doesn't change when you go from here to here, or here to here, or here to here, or anywhere, right? And so that means this whole region in which the electric field is 0, which it will be for a conductor in equilibrium everywhere inside the conductor, the potential must be constant everywhere throughout the volume. Is that making sense? Even if you had a cavity, so long as there's no charge inside the cavity, the potential would still be constant because the electric field will be 0 everywhere inside, right? Even in the cavity, which is surrounded by a conductor. So if this room was a metal room and we were inside, the electric field will be 0 so long as we don't have any charges inside, because only the charges inside can produce an electric field inside, nothing from outside, right? Do you see the inside of a metal is always shielded from outside? What if this was not a conductor? What if in your exam you were given some kind of a conductor that was shaped like this, and there were some charges distributed on this? And suppose we asked you the same kind of question about the potential, what would you say? Anybody has any thoughts? So this is again a conductor or a metal, and you have some charges that you throw on the surface. Anybody has any thoughts on what should be the potential everywhere throughout the volume of this, please? Constant. And again, the electric field everywhere inside should be 0. That is exactly what happens in all conductors in a very short amount of time. I keep saying that, you know, the time scale on which this will happen, you know, if you dump some charges on the conductor, very soon they'll distribute themselves in such a way that equilibrium is established such that there's no net force on any of the free electrons. That means the electric field is 0, right? F is equal to QE. So equilibrium would mean, you can see, equilibrium would mean that net force is equal to 0, and since F net is equal to Q times E, it means E is 0. And that means, again, in equilibrium, the electric field everywhere inside should be 0. And again, if you go from any point to any point, suppose this is your initial and this is your final, there is no change in potential because the electric field is 0 everywhere, so this integral, line integral, will be 0. Right? By the way, will the charges uniformly distribute themselves here on the outer surface? No. Charges will not distribute themselves evenly if this thing is shaped like this. In fact, you will have a higher charge density here. You know, sigma will be more closer to the pointy edge than here, right? Because what is the criteria? The charges will distribute themselves in such a way so that what happens? The electric field everywhere inside becomes 0. That is the criteria for how the charges will distribute themselves on the outer surface. Does that make sense? And so in this case, charges have to be more close to the pointy edge compared to elsewhere. But the important thing is these charges have distributed themselves to shield, you know, to make the electric field 0 everywhere inside, right? And so the potential is constant throughout the volume. By the way, do you guys know of something called lightning conductor? Have you guys heard of something called lightning conductors that are there on tall buildings and things? You know, those things jutting out. What do they mean? What is the meaning of, what are lightning conductors? Anybody, please? Yeah, it turns out, very good. I mean, it turns out that, remember we said that, you know, you could have clouds with a lot of charges on them. And so the electric field in this region could be very large. You know, you could have very high electric field if you have, say, negative charges. You know, you could have some very high electric field in this region. Now there you could have some tall buildings. You know, these are some buildings. What they do in the building is that, you know, instead of, because what could happen? Could the electric field become more than the breakdown voltage of the air? Remember, or breakdown field, electric field. So we said that when the electric field magnitude exceeds 3 times 10 to the power 6 Newton per Coulomb, or the same as volt per meter, if the electric field becomes more than this, then air breaks down. And what is the meaning of breaks down? What do I mean by the air breaks down? That means it starts behaving like a conductor. So that means air starts behaving like a conductor. So in other words, you know, you will see usually air is an insulator, but what starts happening is that you get like plus minus you know, ionization, and then through this air, which now starts acting like a wire or a conductor, charges from the cloud can get dumped onto, say, a building or onto anybody or onto the ground. If you want to make sure ahead of time that it doesn't happen, say, it doesn't get dumped on a building or something, as a preventative measure, what you can do is you can use a lightning conductor, which is a very sharp object like this. You know, it has a sharp edge on the top, and it's close to a building, and it's connected to the earth. It's connected to ground. So it's a metal thing. So this is a lightning conductor. You know, which is made of metal, and it has a pointy edge, and it is connected to earth, it's grounded. What's the advantage of this? It turns out that because of these charges here, suppose you have some, will this negative induce some positives in these regions, maybe some positives here, some induced charges, etc. Yeah, and the point is that so that the electric field inside stays 0, right? Everywhere inside this metal stays 0. Now here is the thing, at the pointy edge, the charge density will be largest. Charge density will be much higher at the pointy edges as opposed to at other places. So if the charge density is largest, sigma is largest at the pointy edge, then the electrical breakdown of the air will happen first in this region. Do you see what I'm saying? And if the electrical breakdown of the air, so that the air starts behaving like a conductor, happens first here, then what will happen is that the charges from the clouds will get dumped onto this lightning conductor, and they'll actually go to the ground. They'll get dumped to the ground because this wire is connected to the ground, and the good thing is then it's not getting dumped on a building or on top of some person or something, and that will save you. But the important thing to realize is that the electric field inside the conductor in electrostatic equilibrium will be 0, but the charge density will typically be higher closer to the pointy edges, in order to make sure that if you add up the electric field due to all these charges and due to all these charges, they add up to give you a 0 everywhere inside, right? Is that making sense? Any questions, folks? Okay, let's move to the next question then. Okay, it's saying consider two isolated spherical conductors, each having a net charge q. These spheres have radii a and b, where b is greater than a. Which sphere has a higher potential? You have 3 choices. Please talk to a person next to you. Your time starts now. Alright, what do you think is the answer? Well, first of all, we have to think about what should be the potential inside of a spherical conductor. First of all, remember, all of the charges will get distributed evenly on the outer surface of this spherical conductor, right? Because this is a conductor, so charges will uniformly get distributed. What we learned last time or the time before was that if you try to find the potential anywhere outside at a distance r away, the potential due to a uniform sphere of charge happens to be k q over r, as though all of this charge was at the center. Remember, just like when we were finding the electric field, it was the same way. So now you can take the limit, keep going closer, 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 closer till you reach the surface. If you reach the surface, the potential, what will the potential be? Say for example anywhere here, if the radius is r, wouldn't it be v is equal to k q divided by capital R, which is the radius here? Okay, now what about the potential everywhere inside? It will be equal to kq over r. Why? Because the electric field everywhere inside this conductor is 0, and if the electric field everywhere inside the conductor is 0, the potential everywhere inside will be kq over r. That's exactly what we were saying all this time here, that potential does not change if the electric field is 0 everywhere inside, right? So basically what we are saying, because here it's asking which sphere has a higher potential. So do you see that since the sphere has a potential kq over r compared to potential of 0 at infinite distance away, then if r is larger, potential will be smaller. Is that making sense? So r increases, potential decreases. You can see that. And because it's saying that q is the same, right? And here it's saying b is greater than a, and so the sphere of radius a has a higher potential. Is everybody clear on this? Any questions about this? So suppose we have a situation like this. Suppose you have a battery which has a voltage of say 3 volt. So it's the potential difference across the battery is 3 volts. Suppose there is a capacitor here. Let's say its capacitance is C1, which is 4 farads. There is another capacitor here which is 2 farad. Let's call it C2. There is another capacitor here which is C3, which is 4 farads. And there is another capacitor here, C4, which is 4 farads also. We are asked to find these things. What is C equivalent? And we are asked to find what is the charge, Q1, Q2, Q3, Q4. Do you think we could do this? By the way, in your book, in some of the problems, you have been told, you're not shown the battery, you're just told, okay, it just says, okay, there is some point A and B, and the potential difference across VAB is equal to 3 volts. It's the same thing. There is some potential difference across A and B, which is 3 volts. It's the same as, for example, me putting a battery there. All right, so the question here is, how should we proceed? Anybody has any thoughts on what should be the first thing we should do? Go ahead, please.
We should combine C3 and C4.
So you're saying the best thing would be to first find C equivalent, right?
Yeah.
Okay, that's a good idea. And you're saying we should first combine C3 and C4? How many people agree with her? Okay, C3 and C4 are definitely clear cut, and they are definitely in what? Series or parallel? Series. Do you see that there is no junction between C3 and C4? There's just one wire. This is just one wire. So C3 and C4 are in series. We can combine them. And if you recall from what we had learned in the past, this is what we learned, that C equivalent for series capacitors, if we had 2 capacitors in series, it was 1 divided by 1 over C1 plus 1 over C2, and C equivalent for 2 capacitors in parallel was C1 plus C2. Do you remember if their individual capacitances were C1 and C2? Is everybody remembering this? Okay, so if she is right, then we can combine these two. Let's combine those two together, and if we combine them together, we end up with this. We end up with a circuit that looks like this. Instead of these two, we have just one thing, and let's give it a name. Do you want to call it Harriet, or C34 will be a better name? Well, let's call it C34. All right, so what is this then? Since these two are in parallel with each other, we can use this, and we can say, oh, this is going to be 1 over 4 farad plus 1 over 4 farad, which is 1 over 2 over 4, which is 2 farads. So basically the equivalent capacitance of these two capacitors is going to be 2 farad. By the way, could I have put this equivalent capacitor anywhere here? So long as I put it in this branch here? Would that be fine? Yeah. So it's okay to say, oh, this capacitor C34 is here, right? Or it's okay to say, it's say here. So long as I put it in this branch. I told you the length of the wire doesn't matter. The shape of the wire doesn't matter. The important thing is it has to be in this branch. Okay, so let's put, this is my C34. C34 is 2 farad. Now what do we know about this circuit? Anybody else? How do we find the C equivalent? We have collapsed 2 of them into 1, and now our circuit looks like this. Can we simplify this further to find C equivalent? How? Anybody? Please go ahead.
C2 to C34 are parallel.
How many people believe that C2 and this capacitor C34, which is equivalent of C3 and C4, these two are in parallel to each other? She's absolutely correct. And parallel means they must have the same potential difference across them, right? One way to figure out that they are in parallel is look at their edges. Look, one end of this capacitor is connected to this wire, and it's meeting one end of this capacitor at this end, and there's nothing in between them. Let's check the other end. This end has this wire connected to it, and this end has this wire connected to it. Hey, there's nothing else in between them. That's good. That means these two are in parallel, right? You know, if there was another capacitor here, let's say C5, could we have said that C2 and C34 are in parallel? No, we couldn't have. We should first then combine these two, which will be in series, and only the equivalent of those two then will be in parallel with this, right? Okay, so in this case we are able to do the parallel combination because of the fact that those two are indeed in parallel, and we can now give it a fancy name. Okay, so this is C1 of 4 farad. We still haven't touched it, and now we have equivalent of 2, 3 and 4, and these two are in parallel. If they are in parallel, can we use this? So this will be 2 farads plus 2 farads, which is 4 farads, right? Is everybody seeing that the equivalent of this and this, which are in parallel, will be 4 farad? Okay, any thoughts on what these two things are in? How many people are convinced that the equivalent of 234, which is 4 farad, is in series with C1? Rose, that's absolutely correct. These two are definitely in series because there's, you see, this is one wire. When things are in series, you know, there's no junction between them, right? The same charge will be accumulating here across the plates and across the plates here. Do you see? Is everybody seeing that? You know, think of this as, suppose there was a battery here, and this is a 3-volt battery. You know, as soon as I close the switch, let's say that there's a switch, as soon as I close the switch, what's happening? The electrons are moving this way from this negative terminal, and electrons will be going this way, and there are electrons accumulating here, right? If electrons where are the electrons coming from? Look, they come like this. So there's going to be equal amount of positive charges accumulating here, right? And then by induction, this one gets negatively charged. Where did these electrons come from? They came from this plate. So this gets positively charged. So basically, is everybody appreciating that the Q, you know, this is plus Q minus Q plus Q minus Q. The Q must be the same for both of these, right? Because, you know, basically the electrons left here and came to this plate, so obviously the amount of positive here and negative must be the same, and then you are inducing these other charges, and these electrons are going from here to here. I want everybody to appreciate that when the capacitors are in series, they have the same charges on them. And notice in this case, the reason they have the same charge is because there's no junction between them, right? Any questions about this? Okay, so at this point we can find the equivalent of these two, and the equivalent of these two will be, let's give it a name, C1, 2, 3, 4, which is the equivalent of the whole thing. These two are in series, so the C equivalent will be, again, you know, 1 divided by 1 over 4 plus 1 over 4, which is 2 farads. So this is just 2 farads. Okay, good. So we found this. We still need to find what is Q1, Q2, Q3 and Q4. First of all, let's figure out what is the charge on this equivalent capacitor. Can we figure out the charge on the equivalent capacitor? How much should be the charge accumulating here? As soon as I close the switch, this capacitor will accumulate some charge. Let's say that this is a 3-volt battery, right? This is the battery voltage. How much should be Q? Anybody has any thoughts? Remember, please. Excellent. Remember the relation Q is equal to C times V. Remember C, the capacitance was the proportionality constant. Q is proportional to V and the proportionality constant is called C. So from here you can see that we can see here, sorry, Q there would be the battery voltage times C equivalent, which is 3 volt times 2 farad, which is 6 coulomb. Very large. So these numbers are not very realistic, but that's all right. So we got 6 coulomb. So basically here we have Q is equal to 6 coulomb. So here it's plus 6 coulomb, here it's minus 6 coulomb, right? Okay, now how can we trace back now? We have to somehow go back from here to my original case. What do you think? Is the charge on this C equivalent will it be the same as the charge on these two at least? Huh? Yeah, it will be, because the thing is, because you can see that these two are in series with the battery, right? So here also the charge will be 6 coulomb and here also the charge will be 6 coulomb. Basically going back, okay, if you look here, you know, let's say that this is my battery here. You can see that the charge that is flowing out here, do you see the same amount of charge will accumulate on this, right? So the Q here, this is Q is equal to 6 coulomb. Now here is the thing, so what will happen at this junction here? You know, because we are saying this thing will have a charge of 6 coulomb. This is this one, right? But what will happen to this 6 coulomb charge when it reaches this junction? Will it split? Yes, it will split. So this charge is going to split into 2 parts here, right? The thing is, typically you will have to figure out how much will split here and how much will split here, how much will go this way and how much will go that way. And the way you will figure out is by realizing that the voltage across this and voltage across this should be the same, right? So typically you will figure out how much charge, is everybody appreciating that? The total charge is 6 coulomb, but the thing is that some of the charge out of it has to go here and some has to go here. It's possible that here it will be only 2 coulombs and here it will be 4, or here it could be 1 and here it could be 5. But let's see what it is in our case. You can already see both of them are 2 farad capacitors. Will the charges equally split? Yes, so I gave you an easy example in which the capacitance of both of those capacitors in parallel is the same. So I know that equal amount of charges should go on each of them. So 6 coulomb will split into 3 coulomb each, right? But typically that's not the case. So let me show you that in your homework you might have, say for example, if this was 1 farad and this was 3 farad or something, in that case you have to make use of this, that V is the same for capacitors in parallel. But what is V? Notice from here, V is equal to Q divided by C. So that means Q1 divided by C1 should be equal to Q2 divided by C2. Is that making sense? In other words, you know, another way to say this means, this implies, if you like, that Q1 should be equal to C1. Well, I mean, I shouldn't have given the name Q1, etc. What I mean to say is C2 and C34. So let me call it C2 and C34. So Q2 divided by C2 should be equal to Q34 times C34, right? And when I wrote Q1 and Q2, I didn't want to confuse you with the names that I had chosen here. So the point is Q2 over C2 should be Q34 divided by C34, and this means that Q2 should be equal to C2 times Q34 divided by C34. In our case, C2 and C34 are both the same. They are both 2 farads, right? Do you see? So for us, this is 2 farad, this is 2 farad times Q34, and that's Q34. So that means we find that Q2 is equal to Q34. This is not a surprise because we knew that the current is splitting up. And we also know that Q2 plus Q34 should be equal to the total charge that enters here, right? And so each of these should be how much charge should be there in each of these plates? Let's say Q2 will be 3 coulomb, and here this should be Q34, that should be 3 coulomb also. Is everybody appreciating how to do it for the cases where Q34 was not the C2 was not the same as C34? You will just make use of this and the fact that Q2 plus Q34 should add up to the total charge that's getting in, which is 6 coulomb. Everybody comfortable with this? Any questions so far? Okay, great. So let's see what we have figured out. So we already know then, we know this is what we call Q1. So we already know the charge here is 6 coulomb. We already know the charge on this one, this is 3 coulomb. Hey, we still need to figure these two out. Is that a big problem? We are given that the equivalent capacitor has a charge of 3 coulomb, right? And these capacitors are in series. What do you think should happen? What should be the charge on each of these? Should be the same? It should be, right? So the thing is, so what we are saying is that this is the charge on the equivalent capacitance of 2 capacitors in series, and each of these must have the same charge as its equivalent capacitance, right? Because these are in series. Is that making sense, folks? So that means each of these is also 3 coulomb. Is that making sense? Any questions about this? So is everybody appreciating that this thing is going to be Q4 will be 3 coulomb, Q3 will be 3 coulomb, this is your Q2 will be 3 coulomb. Is everybody comfortable with this? Any questions about this? Do you see how I figure out which plate will be positive and which plate will be negative for all of these capacitors? Is that clear to you how to do that? Again, you just have to do it in your head and see that you understand what's going on. So think about it. Suppose initially there was no charge on any of these things. Initially they were all uncharged. What do? We shut the switch. As soon as we shut the switch, electrons will start flowing like this. That's the charge we are talking about. Electrons will start flowing. Some of it will go this way, some of it will go this way. But you can see that negative charges will accumulate on these plates, right? Where are those electrons coming from? From this plate. So obviously this plate became positive, right? If this became positive, it will attract negatives from this side. So this became negative. That means these must become positive because the electrons ran away from here, right? And if these become positive, that means this must be negative, and that means where did these electrons come from? They must have come from here, so this will become positive. Is that making sense? Any questions about this? Have you guys tried homework problems like this? I'm pretty sure that I gave several homework problems which were of this sort. All right, any questions about this, folks? All right, let's look at the next topic then. The next thing we are going to talk about is how much is the energy stored between the plates of a capacitor. all right? And it's not a difficult thing to figure out. So if suppose a capacitor is charged with a battery which has a potential difference V, and the total charge on the two plates is, let's say, Q, the question is how much is the electrical energy that is stored, you know, because there is electric field, right? There's electric field pointing from positive to negative plate, and so electric field means that there must be some electrical energy stored in that field. And so let's try to figure it out. So the question is, how much is the energy stored? So here is the thing, let's say we have this capacitor, we have this battery, we have a switch here. Let's say the capacitance of this capacitor is C. You know, this is my capacitor, this is my battery, and let's say battery voltage is V. As soon as I close this switch here, you know, as soon as I close the switch, the circuit is complete now. Electrons will start flowing like this, start accumulating on this plate. Where did these electrons come from? They came from this plate. So this plate now has less electrons, so it's positively charged, and there's equal amount of negative charge there. So there is a charge building up, plus Q on this plate, minus Q on this plate. Let's think about the case where we started from a completely uncharged capacitor. Right? Remember, one thing you do know is work done is negative of the change in potential energy. Right? Don't we know this? Another way to say this is work done is equal to minus Q0 times change in potential. Why? Because the potential energy is Q times V. So why do I want to use this? You know, now we notice what we are trying to find. We are trying to find energy. Why is there energy stored between the plates of a capacitor? You know, what is work done? You know, work done by something means that there must be some transfer of energy from something to something else, right? So in this case, you know, if the battery is doing work, what it's doing is it's basically storing energy in between the plates of a capacitor. So the battery does work to move the electrons from this plate to this plate, so that this becomes positively charged, this becomes negatively charged, and this work done shows up as the stored energy between the plates of the capacitor in the electric field. So what I want to know initially is, let's go slowly. So what we will do is we'll first figure out, as soon as I close the switch and the electrons start getting dumped here, there was a small amount of work done, so an infinitesimal work done by the battery. Let's call it dW. This should be equal to, and I don't care about the signs, folks. I'm not going to worry about this minus sign right now, okay, because I'm only interested in the work done, and I don't care about the sign. So what will this be? If suppose some charge, and we are talking about the charge of the electron, so suppose the electrons are getting dumped, so dW will be equal to Q times a small change in potential dV. Don't care about the sign. This is just coming from here. We are talking about an infinitesimal work done in moving an electron or some charge, these are charges of the electron, from one plate to the other plate by the work done by the battery, okay? So what would be the total work done? Suppose if you have dumped total charge Q on the plates, the total work done should be integral of this, right? So the total work done in dumping the charge Q would be integral of this And initially the charge was 0, and finally the charge has become Q, or let's say capital Q if you like to call it. So we are trying to figure out what is the work done in moving the charges so that the maximum charge on this becomes capital Q. Okay, now what is dV? Can I write dV in terms of dQ? Look, Q is proportional to V, isn't it? So Q is proportional to V because as the charges are being pushed, is there voltage developing between the, so dV, what is dV? dV is the voltage that is developing between the plates of the capacitor when the charge here on the plates is dQ, right? And as you keep pushing more and more, is this dV going to, is the potential difference going to increase because more and more charges are being dumped? And there'll be a point when you have total charge Q here and minus Q here. The question is, how much is the work done in causing a total potential difference, V across the plates of a capacitor? So in order to figure that out, we can make use of this. Q is equal to C times V, and that says that dQ will be equal to C times dV because C is constant, right? Remember, C is a proportionality constant. So that means C will be equal to, so this means that dV can be written as dQ over C. So in other words, in this integral here, we have integral from 0 to Q. We have Q times, instead of dV, I'm going to write dQ over C. Is everybody seeing that C is constant? So I can pull it out. So if I can pull C out, I have 1 over C integral from 0 to Q, Q dQ. Who wants to tell me what is integral of x dx? X square over 2, right? So here it will be Q square over 2. So this is 1 over C Q square over 2, because when you put the upper limit, you will get capital Q square. When you put the lower limit, it's 0. So basically, what have we figured out? We have figured out that the work done by the battery is equal to Q square over 2C. Should that be equal to the energy, that is electrical energy, that is stored between the plates of the capacitor? Yes. So this is exactly, this should be equal to the potential energy stored, if you like, you can call it electrical potential energy, stored between the plates of a capacitor. So what we have learned so far is this. We have learned that the total potential energy stored between the plates of a capacitor is half Q square over C. By the way, if suppose you were not told how much is the charge on the plates, you were told the battery voltage, can you write it in terms of the battery voltage? So if V was given and not Q, how can we write this same thing in terms of V? Can we again make use of this Q is equal to CV? Yeah, we can make use of the fact that Q is equal to CV, and what we can say is that instead of Q, we are going to write C times V square divided by 2C, and this is C square V square over 2C, and this is equal to half C P square. So the potential energy can be written as half CV square. These two things are exactly the same things. This is the same as this. One case you're writing it in terms of Q and C, the other case you're writing it in terms of C and V. By the way, can you also write it in terms of Q and V and eliminate C? Sure. Again, make use of this. Make use of the fact that from here C is equal to Q divided by V. Is everybody seeing? I'm not going to do this out. You can instead of C, write Q over V, and you can see U is now in terms of Q and V. So depending upon what you have been given in the problem, you can write your potential energy between the plates of a capacitor in terms of Q and C, C and V, or Q and V. Any questions, folks? What should be the unit of this, please? Very good, joules. And sometimes in the exam I ask you what is the unit of C times V square, and there are 5 choices given. People have a very difficult time, but the thing is, as soon as you see the combination C times V square, you should know that it should have a unit of joules because it's potential energy, right? So it will have the unit of energy, and in SI unit it's joules. Any questions about this, folks? Okay, then let me now talk about how much is, this is the total energy stored between the 2 plates of a capacitor if you put a charge Q between the plates, right? By the way, this is capital Q. The way we had chosen it, we called it Q. I just want to be consistent with our notation, right? Again, there's nothing in the name, I just want to be consistent. Now I want to figure out how much is the energy per unit volume between the plates. You know that this energy is stored between the plates of the capacitor in the electric field. I want to know, because if you have a bigger capacitor, there's more volume, there's more space between the 2 plates. Volume means space, right? Now if suppose, you know, for example, if I go even increase the distance between the plates or decrease the distance, there's less space and there's more space. I want to know what is the energy stored per unit volume. That means energy per meter cubed. It's easy to do, and that's called energy density. So let's now try to figure out, and this concept of energy density is going to be extremely important because later on we'll talk about electromagnetic waves. And electromagnetic waves, for example, light wave or radio waves or gamma rays or X-rays or ultraviolet or microwave, all of these things basically have an electric field, an oscillatory electric field and an oscillatory magnetic field, and the energy that is stored in the electric field per unit volume will be exactly the same as what we'll find between the plates of a capacitor per unit volume. So this, you know, equation is going to be very useful because this turns out to be a general relation for what is the energy stored between in an electric field. All right, so it's going to be useful even later on. So what I'm saying is let's try to figure out energy per unit volume. This is also called energy density, and we are going to write it with little u as opposed to capital U. So this is capital U divided by volume. And folks, I'm always going to write divided by volume. I don't want to use V for volume because there are too many V's floating around. You might confuse volume with potential difference or voltage, and I don't want you to get confused, so I'll always keep writing U over volume as opposed to U over V. Okay, so in order to do this, let's try for a case that you are very familiar with. Let's try to do it for a parallel plate capacitor. Okay, so for a parallel plate capacitor, like for example this thing here, we have U and divided by volume, and volume will be the area of cross section times the distance between the 2 plates, wouldn't it? The area of cross section of each plate, A, for example here it's circular, so it's pi r square times d. Isn't that the amount of space? If you ask me how much is the amount of space, pi r square times d. That's what we are saying. This is the volume. Okay, what is U? Let's say U can be written as half C V square. Okay, now if we were using parallel plate capacitor, do you remember that C was equal to epsilon 0 A over D, where A is the area of cross section, D is the distance between the plate, and there is air or vacuum, nothing between the 2 plates. So this is what we had learned. Also, if you remember, what, by the way, I want to warn you of one thing. I'm using this symbol V now, and this is the way that your book uses also, but V is really already VAB. We are not talking about potential at one point, we are talking about potential difference. between the two plates of a capacitor. Do you know what I'm talking about? So if we are calling, let's say you call this 0 volt and this is 30 volt, I'm talking about 30 volt minus 0 volt. Or if you decide to call this 20 and this 50, we are talking about 30 volts, the difference. So that V is already the difference, potential difference or voltage between the two plates of a capacitor. So maybe the symbol, I'm not going to keep calling delta V, but it really is delta V. I want everybody to appreciate that every time this V is there, this thing is really delta V. This is potential difference. But we are not going to keep using that symbol. It's just cumbersome. We are always talking about the potential difference between the plates of a capacitor, or voltage. Voltage is potential difference, right? All right. If you want to call it delta V, that's fine. All right, so the thing is, what was this V in terms of electric field? Does anybody remember the relationship between electric field and potential difference? Remember, we can make use of that relation. Remember, we can say V final minus V initial is equal to minus integral E dot dl. E was constant between the two plates of a capacitor, wasn't it? If the plates were big enough, you can pull this out. So what we got is V final minus V initial. You know, let's just write it as delta V was equal to minus E integral dl. And integral dl, the angle between the electric field and dl can be taken to be, you know, 0. So cosine 0 is 1, right? And integral dl is just the distance between the plates if you're talking about going from one plate to the other. Isn't that true? So here delta V is minus E times d. Is everybody with me? This is something we have done in the past 3 times already. This is the 4th time I'm doing the same thing. But it's very important. So the thing is, so what I'm showing you is that delta V, by the way, we are not going to worry about the minus sign here, so let's just worry about the magnitude. And what I'm saying is that delta V is what we keep calling V now. This is the new name. And so you can see that instead of this, I can write this. This is half. Instead of C, I can write epsilon 0 A over D. Instead of V, I am going to write electric field between the plates times D, and this electric field is constant. So V is the magnitude of electric field times the distance between the plates square. Is everybody with me? The potential difference is the magnitude of electric field times the distance between the plates square, and divide that by A times D. I hope everybody can see. Let me erase this. I hope everybody can see here that this, what we have here is this half epsilon 0 A electric field square D square divided by D times A times D. You know, this D, this A, this D, there are 3. This D, and this D square get cancelled. This A and this A get cancelled. You see? So what am I left with? I am left with half epsilon 0 E square. So this is a very interesting result that I said it will always be true. What you find is that the energy stored in an electric field per unit volume is always equal to half times epsilon 0 times electric field square. And this is what you'll see later on when we start doing electromagnetic fields. So what we see is this half epsilon 0 E square. This is energy density. And this is for any electric field. That's the great thing about this result. Even though we derived it for parallel plate capacitor, it turns out this is the energy density or energy per unit volume whenever you're talking about how much is the energy per unit volume in an electric field. Even for the case of light waves, how much is the energy stored per cubic meter in a light wave which has certain electric field. I can figure that out if you tell me how much is the electric field of the light wave here in this volume meter cube, right? So this is a very general formula. Now again, what should be the unit of this? Somebody from the first row, what should be the unit of energy per unit volume? Very good, it should be joules per meter cube. And one of my favorite questions is sometime or the other, either in midterm or final, you will see it will ask you what is the unit of epsilon 0 times E square, and it might be give you 5 choices. I'm telling you, these questions are extremely hard. It's not an easy question. So I want you to think about the fact that epsilon 0 times E square has the unit of joules per meter cubed, right? Because it's energy divided by volume. So SI unit is joules per meter cubed. Okay, I'm not going to plug in numbers, but does everybody see that if I give you that the electric field between the plates is say 2 newtons per coulomb, how much is the energy per unit volume? All you have to do is put 2 newtons per coulomb square times epsilon 0, which you know is a constant, right? 8.85 times 10 power minus 12 in SI unit, and you will find how much is the energy stored per unit volume between the plates of a capacitor in joules per meter cubed. Anybody has any questions? All right, then we'll now talk about the last topic of this chapter, and that is dielectrics. Does anybody know the meaning of the word dielectrics? Have you ever come across this in any other course? What does the word dielectric mean to you? Because once I tell you what it means, you'll say, oh, now I get it. But the thing is, what do you think it means? Never heard of dielectrics? Okay, the word dielectric actually is the same as the word insulator. So it's just that we use this word dielectrics. So whenever you're talking about dielectrics, you're talking about insulators. And in all insulators, if you put an insulator in an electric field, remember we said that insulators don't have free electrons. So it's not like the electric field everywhere inside will be 0. That's not going to be the case. But what will happen is that at the atomic level, at the level of atom, there'll be some small charge separation, right? And that's what we call polarization, remember? So keep that in mind, and now let's think about what will happen. So here is a capacitor. Right now, all of this formula that we had derived, when we said that the capacitance of a capacitor is epsilon 0 A over D, that was when between the two plates I had nothing. Vacuum means nothing, or you can say we have air, because it turns out air is has such a small dielectric constant. In other words, it behaves pretty much like vacuum, as though there was nothing. But now suppose I put this thing here between the two plates. Suppose I put this thing here. Suppose I put this book here. These are all different kinds of insulators. Aren't they made of insulating material? Suppose I put this thing, or I put this thing. Do you think anything will change? Let's try. In fact, I want to first charge these plates, this plate, and then see if anything happens at all. Folks, watch. Is there a potential difference there? Okay, good. Now, notice what will happen if I bring this thing here. Did anything happen? Huh? Sorry. Okay, you see some potential difference, right? Okay, let's try this. Nothing? You see nothing here? Okay. Okay, let's try now. Anything? Huh? Okay, changed a little bit? Okay. So let's think about which way should it change. Should the potential increase or decrease? What happened? It turns out that when you put a dielectric material, that means when you put an insulator between the plates of a capacitor, it could be wood, it could be plastic, it could be water, anything. Water also, pure water is an insulator. Only water that is not pure starts behaving like a conductor, but pure water is actually an insulator. So the question is, what happens when you put a dielectric between the plates of a capacitor? And just for simplicity, let's not worry about the fact that this was being put only in a small region. Let's assume that we filled the whole region between the plates with this material. All right? We are going to now define something called dielectric constant of a dielectric or insulator. Okay, so basically, when I put a dielectric between the plates, so here is one plate, here's one plate, and here I'm putting now some dielectric material. It turns out we can define something called dielectric constant, kappa. This is a Greek symbol, kappa, looks like K, which is a constant for a given dielectric. For example, for water, kappa will be 80. And this tells you how much will the capacitance increase when you put the dielectric in. So for example, the capacitance with dielectric will be equal to kappa times the capacitance with vacuum or air. Do you see what I'm saying? And kappa is always going to be greater than or equal to 1. Kappa is equal to 1 for vacuum or air. I mean, for air it's pretty close to 1. It's basically 1.0000 something, you know. So for all other materials, kappa will be greater than 1. So for example, kappa for water, as I said, is 80. For different materials, it's different things. So what does it tell you? That means as soon as I put a dielectric in, what happens to the capacitance, folks? It will go up. Do you see, if kappa is always greater than 1, as soon as I put the dielectric in, the capacitance will go up. So for example, for a parallel plate capacitor, how much will it go up? Tell me what will happen for a parallel plate capacitor? Remember, for parallel plate capacitor, you know, capacitance with vacuum was what? Epsilon 0 A divided by D, wasn't it? Do you remember we had found it a few classes ago? Okay, so then what should be the C with the dielectric? Let's say that the whole region between the two plates is now filled with, say, water. How much would be the capacitance now? Here. Should it be kappa times that number? Yeah. So now it will be, you know, kappa times epsilon 0 A divided by D. So for example, for water, the capacitance will increase 80 times if kappa is 80, right? So basically what you can see is that if you put a dielectric between the plates of a capacitor, what you're changing is the capacitance. And capacitance, remember, is this, Q over V. That means the amount of charge that you can store per unit voltage is increasing if you put some dielectric material. You see? So that means if you use a 1 volt battery to charge the capacitor, and if you have a dielectric, you will be able to store more charge. There are two cases, okay? Let's talk about two cases. So when you keep voltage fixed, voltage means potential difference fixed, by keeping the capacitor connected, to a battery, So here is the thing. So suppose you have this capacitor and here is a battery. This is not, you can't see this picture very well, so let me redraw it. So, okay, so here is a battery, this is my battery, and this is my capacitor here. And this capacitor has some capacitance C vacuum, right? That I can figure out by knowing what is the area of cross section and what is the distance between the plates. Now what do you think will happen if I put some dielectric over here? Now I'm going to shove some dielectric in. What happens? C increased and C became C dielectric, which is equal to kappa times C vacuum. Isn't it? Hey, what effect do you think that will happen on the amount of charge that I had over here? So let's say that Q initially, this was plus Q here and this was minus Q here, and this was the charge that you had when you had vacuum before you put the dielectric in. So this was the charge. Now the question that I have for you is, once you put the dielectric in, do you think anything will change? Can the voltage change? No, if you have connected it to say a 3-volt battery, then the voltage here will be 3 volt, right? Is that true? Till the charges stop. So the thing is, till the movement of charges in this thing stops. So basically what we are saying is that in this case, since we have connected it to a battery, this thing is locked in with 3 volts. So the question is, as soon as I put water here or as soon as I put wood between the two plates, what do you think will happen to the charges? Should Q change? Because one thing we know is Q is equal to C times V, right? Isn't that true always? Q is equal to C times V. That's always true. So if Q is equal to C times V, you know, old case was Q old was equal to C old, which was C vacuum, times the battery voltage V. And the new situation is, what's the new situation? Okay, the new situation is we have some Q new now that should be equal to C dielectric, because we have shoved some dielectric between the plates, times the same voltage because we have fixed the battery. We are saying no, we'll keep the battery connected, and it's a 3-volt battery. So what do you think will happen to Q new compared to Q old? Do you see that Q new should be more than Q old because C dielectric is more than C vacuum? Okay, so Q new here greater than Q old if V is kept fixed. Any questions about this? Everybody understands this? Because you will also have some homework questions related to this. Now case 2 is this. Battery is disconnected before the dielectric is introduced. So in this case, the charge is fixed. And actually this case is very much like that, because here you know what I did? I actually charged this with a certain amount of charge. Now the charge is fixed there, right? And what did I do? Then I said, oh, let me bring this and let's see what happens because of that. So the point is, charge was fixed here. I'm not changing the charge because charge is fixed. What am I changing? Is everybody sees that if the battery is disconnected, suppose I have a capacitor like this with some charge Q. You know, this Q is fixed. Good. What you again have is that, you know, you have this. Q should be equal to C times V. This time, as soon as we introduce dielectric, so what we do is So this is the old situation. This is the new situation. In the new situation, we have dielectric here with some dielectric constant kappa. But Q is fixed. I'm not connected. I'm not letting any current flow in this circuit. There's no battery here. There's no current flow in the circuit. Here, do you see that as soon as I introduce the dielectric, what do you think will happen? Will there be a current flowing again so that the charges rearrange themselves such that the voltage again becomes 3 volt in this case? On the other hand, here there is no battery in the circuit. So Q is fixed. So if Q is fixed, so this is C vacuum, this is the old case. Then what you have is Q is equal to C dielectric times V new. This is V old. So you are saying, does everybody see that Q is fixed here? Because I just have this. You know, I put some positive charge here, I put some negative charge, there's no battery anymore in the circuit. Q is fixed. Of course, if you wait for a long time, then these things can get neutralized with some free charges in the air, but let's just ignore that for now. So then for at least some time, the charges are fixed here on the plates. Now if I introduce a dielectric, what would happen? And the point is, if Q is fixed, if this thing is fixed, then as C increases, V should decrease so that the product of the two stays constant. Right, folks? Is that making sense? Is this making sense that C dielectric is more than C vacuum? So V new should be less than V old. And that's what you were seeing. When we introduced this thing, did you see that that thing decreased? So basically the idea is that C dielectric is greater than C vacuum, and that means V dielectric or V new should be greater than V old, V vacuum. Sorry, the other way around, such that the product of the two stays constant. Anybody has any questions about this? Okay, so here is the thing. Why is it, what does the dielectric really do? If I put an insulator between the plates of a capacitor, what is it really doing? Let's think about it microscopically so that we really understand what's going on here. Okay, so let's think about a microscopic view of dielectrics. Okay. By microscopic, I mean, you know, let's look at a very detailed atomic level view of dielectrics. So here is what I have. Let's say that I have a capacitor with a positive plate and a negative plate. So this is plus Q, that's minus Q. Initially, there was vacuum. There was nothing. Now I'm putting, let's say, some dielectric here. It's true that dielectric is an insulator, it's not a conductor. So electrons cannot move macroscopically, they cannot move long distance. But if I look at the level of atoms, you know, these, I'm trying to draw some atoms. Of course, they look too big, but the thing is, if suppose these are atoms, what will happen? Is something going to happen? First of all, is there any external electric field due to this plus and minus charge? Wouldn't there be an external? If you have a plate with a plus charge here and a minus charge here, wouldn't there be an external electric field, E, which has a magnitude sigma divided by epsilon 0, where sigma is the charge per unit area on the plates? So that's the E external due to the charges on the plates. Now, will that do anything to the dielectric, these atoms? What will it do? Anybody? Folks, all of you should be able to tell me what this will do, because this is what we've been learning from day one. Please.
They're going to shift to the right.
Very good. What you will see is that since these are positive charges, basically electrons will move a little bit to that side. They will feel a force. So the electrons at the atomic level will get a little bit tugged towards the positive, wouldn't they? And this is what we call polarization. Remember, we have discussed this several times in this course. Even in the first chapter, we had this idea that in a conductor, these things will happen on a large scale, right? Charges can really go one end and leave behind positive charges at the other end. Here, it's going to happen at the atomic level, right? This is what we call polarization. Now, what is this polarization going to do? If you look at the level of an atom, is there now an internal electric field within an atom itself? Remember, an electric field points from positive to negative charge, right? So wouldn't you say that there is also an internal electric field, E internal, at the level of atom? You can call it E atom if you like. So there will be an internal electric field in each of these atoms that's pointing this way. Is that making sense because of the separation of charge? Okay, so if this separation of charge causes an electric field from the positive towards negative, what I want you to tell me, what happens to the net electric field in this region between the two plates? So remember, there's an external electric field due to these positive charges and these negative charges. And this external electric field, E, which is sigma over epsilon 0, this causes force on the electrons within this atom. They move a little bit on this side compared to the nucleus, and so there is an internal electric field. So if I ask you, tell me just a cleaner picture, in the cleaner picture, what happens to the E net between the two plates, what will you say? Should it be less than or more than E external? Go ahead, please.
Less than.
Why? Because?
Because they're pointing in opposite directions.
Very good, because the internal field of the atoms is pointing in the opposite direction. So E net should be less than this, E external, right? Another way to say this, E net should be less than E vacuum. Because if there was only vacuum, then this was the only electric field. There is no atom to polarize. And for air, we can assume it's pretty close to vacuum. Polarization is so insignificant, you don't have to bother. Does that make sense? Okay, so we are seeing that E net, another way to say this is E dielectric should be less than E vacuum, because the electric field due to this polarization of the atoms is in the opposite direction once you put the dielectric compared to the external electric field. So the E with, this is the net electric field with dielectric, that will be less than E with vacuum, which was just due to the charges on the plates. How much less? It turns out that E dielectric has a magnitude which is E vacuum times divided by kappa, the same dielectric constant. Do you see that since kappa is always greater than 1, if you have anything other than air, C dielectric will be less than E vacuum? Is everybody appreciating that E dielectric will be less than E vacuum if you have any dielectric material, because of the fact that kappa for all of the dielectric materials other than air is greater than 1. In fact, even for air it's like 1.0000 something, but we can assume that it's 1, same as vacuum, so that means there is, you can ignore it. Now, what about the potential difference? Remember, we already talked about it somewhere here. We said that the potential difference, what was the potential difference between the plates? Let me write it over here. So remember we said delta V should have a magnitude of E times the distance between the two plates. This came from this. This came from delta V is equal to minus integral E dot dl from initial to the final. I'm not going to worry about the minus sign, so I just took the absolute value. And what I said is that if the electric field is constant, you can pull it out, which it is for the parallel plate capacitor, and you get this, right? Do you see that? So what happens to, and delta V is what we are calling V. This is a new name for us. V means delta V. It means potential difference between the two plates. Okay? So what we are seeing is that V is equal to E times D, right? So V vacuum will be E vacuum times D, and V dielectric will be E dielectric times D. So which one is more? Who wants to tell me, from looking at these two things, what should be the relationship between V dielectric and E dielectric? Oh, sorry, V dielectric and V vacuum. Somebody from the last row. It is a trivial exercise. You have to look at this. E dielectric is E vacuum divided by kappa. You have to look at these two relationships that tell you what is the relationship between E vacuum and E dielectric, and V vacuum and V dielectric. Tell me what that should be. Anybody? Anybody? Go ahead, folks. Oh, I'm sure all of you can do it. Go ahead, please.
V dielectric would be less than V vacuum.
And will it again be divided by kappa? Isn't it? Because one way to say it is, let's divide this by this. If I divide this by this, do you see that dividing this equation by this equation gives me V vacuum divided by V dielectric is equal to E vacuum divided by E dielectric, because D cancels out. Do you see that? And then we know E dielectric is E vacuum divided by kappa. So if you like, this E dielectric, so this is equal to E vacuum divided by E vacuum divided by kappa, right? And so this divided by kappa makes it kappa. This and this get cancelled. So basically what we have here, you can see, is V vacuum divided by V dielectric is equal to kappa, and that immediately, if you cross multiply, V dielectric goes here, kappa goes here, you get V dielectric is equal to V vacuum over kappa. Is that making sense? So basically, I want you to have a physical picture in mind as to what is going on. When you put a capacitor, when you put some dielectric or some insulator between the plates of a capacitor, the electric field, the net electric field with the dielectric is smaller by an amount kappa. The net potential difference with the dielectric is smaller by an amount kappa, and the capacitance now has gone up. The capacitance with the dielectric is more than the capacitance without it. Does that make sense? That's what we learned somewhere, that so what we learned is that C dielectric is equal to kappa times C vacuum. So is everybody comfortable? Everybody has this knowledge organized, that with a dielectric you have this charge separation which reduces the electric field by this amount, by an amount 1 over kappa. By an amount 1 over kappa, the potential difference between the plates decreases, and the capacitance has now gone up as a consequence by an amount kappa. Any questions about dielectrics, atomic view, what's going on with the dielectric? Okay, so we are pretty much done with this chapter. I wanted to show you a demonstration here, which I think most of you as a kid have already seen. Have you seen this demonstration with Van de Graaff generator? This is a device that has a that can have a, if I turn this thing on, it can have a very, very high, but it turns out that charges, there is this belt, and what it does is this belt actually dumps charges inside this conductor, but since this is a conductor, will all those charges that are being dumped inside, will it go to the outside? Yeah, in electrostatic, you must have done an exploration and seen that too, that even if you touch some charged thing inside to the inside surface of something, it will immediately go to the outside surface, right? And that's the idea that is being used here. So even though this charged thing is dumping charges to the inside surface of this, that charge immediately goes to the outside surface, and very soon the charges are so much that the potential difference on the dome becomes 500 kilovolts. That means, you know, 500,000 volts more than the ground. Okay, so compared to ground, it's 500 volt. In fact, if I touched it with my hand, I don't have the courage, my hair would stand up, you know. But let me discharge this thing. You know, did you see what happened? That was electrical breakdown of air. You know, the electric field is becoming so large between these two things because of those charges. This is spark. This is like lightning striking, or when you touch a doorknob, remember charges jump. Remember we have talked about the electrical breakdown of air. When the electric field becomes more than 3 times 10 power 6 volts per meter, you have breakdown. So instead of my hair standing up, if somebody has the courage, they can come and do it themselves. But because high current can be really lethal, but here the voltage is high, but there's no current. You know, that's the good thing. You know, there's no complete circuit. Otherwise, it would have been dangerous, you know, if we had completed a circuit or something. So let me show you. What do you think will happen? Yeah, that will stand up because, you know, it will get repelled by the charge. And so you can see that it's standing up. Now, if I bring this thing close, you know, I can discharge it again. You see that I'm discharging it. But is everybody seeing what's going on here? It's basically getting repelled, right? Because it's picking up the same amount of charge. Okay, let me now show you something else. And I will first ask you what will happen. In fact, you've already done an exploration which is very similar. So now what I'm going to do, let me take this thing off here. Okay, I am now going to do, I'm going to connect this thing to here. There is a magnet on top of this so that it will stick there. And now this is a wire, a conductor. So I'm making this charge here, you know, charge thing there, connected to this. What do you think will happen now? Any thoughts on what might happen? See, now this is a conductor with a lot of charge, right? When I turn it on, some of these charges through this wire, won't they go to the top thing here? What will that do to these little styrofoam pieces and you know, those metal balls? Will they attract? They'll get attracted there, right? Won't they get attracted? Once they touch it, what will they do? They'll pick up some of the charge. Once they pick up some of the charge, then they now have the same kind of charge that this top plate will have, won't it? And then they'll get repelled. They'll get repelled, they'll go and drop to the bottom surface. They'll give the charge to the bottom surface, right? And then they'll again get attracted to this surface. Then again they'll pick up charge, they'll go down. So what those little metal balls will be doing is they are transferring charge from the top surface to the bottom surface, right? Let's try and see. Do you see it looks like a hailstorm? So by the way, I want you to also tell me what will happen in this experiment. Here there are some things inside the cage and some things outside the cage. Is the electric field going to stay zero regardless of how much charges get dumped here on the surface? So will you see any action inside? No. Will you see action outside on these? Yes. Let's see if that's really the case. See, do you see that, you know, as the charges from the dome are getting transferred to the surface of the metal cage, the outside styrofoams are getting repelled, right? And they are standing out, but inside nothing, because that's a metal cage. Metal cage is shielded from anything that happens outside and on the surface, because these surface charges are distributing themselves in such a way that the electric field everywhere inside stays zero. Doesn't it? Is everybody appreciating that? Any questions about that? Okay, last experiment. So here, let me ask you what would happen in this situation. You know, here we have very, very pointy edges. If I connect this thing to this, First of all, I already want to tell you that you know that this is a very highly charged thing. I told you this is 500,000 volt compared to ground, very high voltage because of the high charges that accumulate there because of all this belt sending charges. So belt is rubbing and picking up charge, and then it keeps dumping it on the inside, which goes outside. Now some of that charge will get transferred through this metal wire onto this. Now since these things are so pointy, remember, just like the lightning conductor that we were talking about, and we were saying that at the pointy edges, you know, the charge density becomes very high and the electrical breakdown first happens there. So there will be electrical breakdown that is going to happen there, and you will see some discharges, and maybe if I don't turn off the light, you may not see those discharges, but there will be basically discharges happening here. If there are discharges happening at these pointy edges this way, what do you think, which way do you think this thing is going to start turning? In the opposite direction. From Newton's third law, if this is sending out some, you know, charges this way, wouldn't those things exert a force in the opposite direction on it so that it starts rotating in the opposite direction? Let's try and see if that's what really happens. Do you see it starting to rotate in the opposite direction to the direction which it's spewing out charges because of the discharge of the air? Okay, actually one more, I have one more experiment, and that is this tube light. You know, the tube light requires a very high voltage, you know, say 1000 volt or something to light it. If I put it close to this, remember we said this is at a very high potential. Do you think this might light up? Let's try. I'm not sure if you can actually see it. Maybe you can't see it. Wait. Let me just turn off the light and show you. Maybe you can see it much better. Okay, so let's see what happens to this. Oops. Not too good, is it? Oh yeah, here. Do you see that? Do you see that it's lighting up? So the potential here is so large on this dome, it's 500,000 volt, that potential difference is enough to light up this this tube light. All right, folks, have a great day.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.